Bismillahirrahmanirrahim. I suggested last time that there are many different types of proofs in geometry. And last time I talked about two types of proofs, and these were flow proofs and flow diagrams and paragraph proofs. So last time I talked about flow proofs and paragraph proofs, which are very similar. Basically, you pick the flow proof and write it in paragraph, and you get your paragraph proofs. And in regards to the flow proofs, I had given this particular example. I suggested that prove that if 2 times the quantity x plus 5 minus 3 is equal to 13, then x is equal to 5 and x is equal to 3. And I had the instructions there, however, were to write a flow proof. Instructions here are to write a 2-column proof. Now, last time when we did this, I had done the flow proof for this, and here it was. And I had suggested that when you're trying to write a flow proof, first you write the given information, and then you write what you're trying to prove over here like this. And then you write the flow proof over here like this. So this was the given information, and you rectangulate it to make it look pretty. And then you take each particular step, and you give the reason for each particular step, and you write it down over here. So the reason for this step is written over here. The reason for this step was written over here. The reason for this step was written over here. And it's very important to supply the reader the reasons that you took every step, and the reasons are given here. Addition property of equality for real numbers, and division property of equality for real numbers, substitution property of equality for real numbers. So for here, for example, I subtracted 5 over here from both sides like that, right? So the reason we were able to do this because it was a substitution property of equality. That is A equals B, then A minus C is equal to B minus C. That was the substitution property of equality. Now, this was a flow proof. Today, we shall learn about 2-column proofs, which are the most common and in a way most methodical proofs in geometry. Writing a 2-column proof is actually not much different than a flow proof, except the flow of the proof is written in 2 columns. So the first thing that we're going to do over here in writing a 2-column proof is we're going to draw 2 columns. That seems natural enough. So here's the 2 columns. And the columns are set up in such a way that over here we write all the statements, and here we write the reasons for the statement. So whenever you write a 2-column proof, you make these 2 columns, and you always label the columns as statements and the reasons given. And over here, every statement goes over here, and here you list all the reasons for those particular statements. That is, all of these reasons will fall into here, right? And all the statements, which are these, will fall into here like this. Okay, so that's the nature of a 2-column proof. I'm going to use the same example actually to suggest to you how 2-column proofs work. And this is particularly important. I could have given you a different example, but one of the key things in geometry, in my mind, is to take an example and kind of almost like to the point that you've memorized the example, to appreciate the example to a certain extent, that the logic of the question flows seamlessly in your mind to the point you almost memorize this, because the logical reasoning is replicated in numerous different problems. So it's very important actually to really understand each example as much as we can. So I'm going to in fact use the same example to hone in our skills. So as with most geometry proofs, the first thing is usually a good idea to write down what's given to you. So here, this is what's given to us, right? So to be given that 2 times the quantity x plus 5 minus 3 is equal to 13. So, and I number each particular statement because over here I write the corresponding reason. So here I wrote the statement, and the reason for statement number 1 will be listed here. So the reason this is true is because this is given information to us. Okay, so this is given. Statement and given. And then what did we do? We were trying to prove this, right? So then the next thing we did was I subtracted, or I added 3 to both sides like this, right? So I added 3 to both sides. You don't have to do the math here because this is a geometry problem anyway. You can write the next statement. That's 2 times the quantity x plus 5 is equal to 16. And the reason this is true, is the reason we can do that, we have the ability to do that, is because of addition property of equality. So addition property of equality for real numbers. Okay, now I have suggested the reasons go over here, right? And the reasons that we should bring forth for any particular geometric argument will either be definitions, or they will be properties, or they would be postulates or axioms, or they will be theorems. So from here on, every time we define something, we really have to memorize the definition in a very precise, accurate method. So you can't like fudge a definition in geometry. You really have to know its adjectives and verbs and nouns and precisely. And properties, anytime we come across a property, we're going to memorize the property. Anytime you come across a postulate, an axiom, we're going to memorize it. And anytime you come across a theorem, we're going to memorize it precisely, because that makes a very big difference. So proofs in geometry are built on these things. So definition, properties, postulates, axioms, and theorems are our best friends in proving things. So we have to really memorize them. And once we did this, and the third step in our proof was that we divided both sides by 2, and we got x plus 5 is equal to 8, and this we were able to do because of division property of equality for real numbers. Now every time I say this, I say it's for real numbers. I don't write that because it becomes cumbersome, but all these properties are regarding real numbers. Okay, for example, very soon we shall learn that there is a reflexive property of congruence for segments. There is a symmetric property of congruence for segments. There's a transitive property of congruence for segments. We have already learned that there is a reflexive property of equality for real numbers, reflexive property, symmetric property of equality for real numbers, and transitive property of equality for real numbers. But the same properties we will extrapolate to segments, and in fact, same properties will extrapolate to angles. So, as I suggested previously, these properties will build on themselves, and they recur again and again. So it's kind of important to get to know the verbiage verbatim, the language in a very precise way. So this was because of division property of equality, and this is for real numbers, and we should appreciate that this is regarding real numbers. And the final step here was that we subtracted 5 from both sides, and then we got x is equal to 3. And the reason for 4, the reason for this particular step was subtraction, SCBTRA. I should spell this out because somebody could say this is substitution, right? So subtraction, we don't mean substitution, we mean subtraction property of equality for real numbers. And you're done. So this is introduction to a 2-column proof. So this is a 2-column proof. So here we have a flow proof where it has its own particular merits, and here we have a 2-column proof, and you can see the merits of a 2-column proof. It's very beautiful and elegant in the sense that everything is very organized. All the statements are over here, and the reasons for every particular statement is given here. So you can talk about every particular step in a very organized way. So if you wanted to bring somebody's attention to step number 3, you can say, look at step number 3, where we have x plus 5 is equal to 8, and that was because of division property of equality for real numbers. So the setup for a 2-column proof has been tested and tried over time, and has become very popular because it is such an elegant way of proving things. Inshallah, next time I shall build on this. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.